So this video is 2 of 3, starting with number 5 from the E2 set, E2 paper 2 set. So 5, an experiment to investigate photoelectric effect. A beam of monochromatic light is incident on a metal surface. When the frequency of light is less than a certain threshold frequency f0, no electrons are emitted from the surface. How does this support the photon model of light? I feel like sometimes these mark scheme explanations go backwards. But I would say this is the first point. If the photon energy, the energy from the photon, is less than the work function, then you're not going to release an electron from the surface. You have to overcome the work function in order to even release a single photoelectron from the work surface. So the kinetic energy of the photons is equal to h times the frequency minus the work function. And again, the intensity of the light has nothing to do with how the kinetic energy of the electrons. So it's like, okay, but what does that have to do with the photon model of light? Note that it's at hf, the frequency. The photon energy is proportional to its frequency, which is the photon model of light, that hf. That the energy is quantized in photons in quantities of the Planck's constant h. So there you go. Here's our setup. We have a variable power supply with a voltmeter on it, an ammeter to measure the electron flow. There's a beam of light on a metal surface, and there's a collecting plate. It says the graph shows the variation of current with voltage for a wavelength 430 nanometers. What graph? This graph. What does it say, 430 nanometers? So before we move on, I want to talk about this graph because it's interesting. So we know that the stopping voltage is when the current is equal to 0. And so this stopping voltage looks like it's about negative 0.9 volts. But again, I want to talk about the graph and what happens if we change things, right? So for wavelength, what if we went with a shorter or longer wavelength? So for the maximum kinetic energies you can get on the collecting plate, basically like right to the point when you're getting just barely like the most energetic electron because you're pushing against it with the electric field. That electric field is represented by V stop. So the charge times V stop is hc over lambda minus the work function. Now the work function depends on the material that you're using. But we can see from the equation that the shorter the wavelength, the more energy there is. So if we change the wavelength, if we decrease the wavelength and make it shorter, it's more energy, so the QV stop is going to increase, meaning that the V stop will have a greater negative value and that curve is going to shift to the left. But if there's an increase in wavelength, then there's less energy. V stop doesn't need to be as strong, so it's going to have a lesser negative value, and that curve is going to shift to the right. But another thing about what happens when you change the wavelength or the frequency. So yeah, since the intensity is constant, if you decrease the wavelength and the power over the area is constant, then the energy rate has to be constant. So if I decrease the wavelength, then each photon has more energy. But if your energy rate is constant, you can throw out fewer photons because your rate of energy is the same. So if I have a more energetic photon, I can throw out fewer of them because the rate of energy needs to stay the same. So if there are fewer photons, then I'm going to get fewer electrons, and the current is actually going to decrease. If I increase the wavelength, the opposite will happen. There's less energy per electron, the power is constant, so I can throw out more photons, I can get more electrons, and the current is going to go up. But notice what I said before. A decrease in wavelength or an increase in frequency means more energy, so the QV stop is going to increase, and the V stop is going to have a greater negative value, and the curve is going to shift to the left. But the current is going to decrease. If I decrease, I keep pausing and then I forget what I say. So if I repeat myself, I'm sorry. Decrease in wavelength is going to shift the stopping voltage to the left, have a greater negative value, but it's going to produce less current. If I increase the wavelength, the stopping voltage is going to shift to the right, and so the curve is going to shift to the right, but the current's going to go up. But what happens as a result of this is that the area under the curve is going to remain constant, Why? Well, take a look at the graph axes, voltage and current. And what is voltage times current but power? Didn't I say the power was constant? That's the area under the curve. Now that's a whole heck of a lot to change the wavelength, so I haven't seen any questions where they talk about changing the wavelength, or if they do, they talk about what effect that has on the kinetic energy. Do not ask, or haven't seen any questions that ask about the effect on the current and the voltage. But I wanted to explain that because I think it's interesting stuff about photoelectric effect. So thank you for coming to my TED Talk. I'm calling this TED Talk is called How Changing Wavelength or Changing Frequency Affects VI Curve. All right, great. Did I say TikTok or TED Talk? There should be a TED Talk TikTok. Probably is. Anyway, I'm like losing my mind over here. Okay, well, I'm not done talking about this graph. I have a couple of other notes, but I feel like that's the most complicated one. What about changing the intensity? So increasing the intensity, which is the power over the area, will increase the current, but it will not affect V-stop, because QV-stop is HF minus the work function. And so the intensity plays no role in there. But also, going back to what I said about how the area under the curve represents the power, increasing the intensity will increase the power. And so if I have more current, that's going to get me more area under the curve, because it will like give me the same stopping voltage, but it's going to give me like a bigger curve, so it's going to give me more area under the curve, hence more power. And then you could say, well, what about changing the voltage? But changing the voltage is exactly what's happening in this graph. Notice that the voltage is the dependent variable. Voltage is the thing that's being changed in this graph. And we talk a lot about V-stop, the voltage value, when we stop the photoelectric current. But I want to talk about, what about when the current is zero? When the voltage is zero, why is there still a current? Because photoelectric effect happens whether there's an electric field between the plates or not. So when I see that the voltage is zero, it's getting me a current of about 18 nanoamps, right about there. So 18 nanoamps of electrons are making it across the gap from the illuminated plate to the collection plate, and there's no electric field coming out of the battery at all. There's no applied voltage. So really what's happening here is that we're changing the voltage from negative, going negative all the way down, pushing the negative voltage is pushing against the photoelectrons. It's trying to push them against the collection plate so that none of them make it. And eventually we do hit a value when 0 photoelectrons make it. The very threshold is right here. That is the stopping voltage. When we actually get the voltage pushed to the point that we're going against the electrons. So in that case with a negative voltage, so if those are the plates, the light is hitting a positive plate and there's a negative plate on the other side that's actively pushing against the photoelectrons. Some of those photoelectrons have so much energy, though, that they cross across anyway against the negative field and strike that plate. That connects the circuit and it represents a current. And that happens in this section here to the point that there is no voltage. Then we switch. We're still illuminating the collection plate, but now the collection plate is negative. Illuminating the photoelectric plate. And that plate is now negative and the collection plate is positive. So the collection plate is like, yo, electrons, come over here. And so now more photoelectrons are going to go to the positive plate. I was like, but now what does that mean in terms of the graph? Notice this asymptotic max value here. This max current. That looks like it's about 44 nanoamps. So at that max current, that's the positive voltage value where you make that the collection plate so positive that it's collecting every single photoelectron that you can get. Maximum saturation. So increasing the voltage isn't going to do anything. You're not going to get any more current because that plate is now so positive that it's collecting all the photoelectrons. Okay, I wanted to explain that. I thought that was important, but let's get back to the actual questions. All right, so explain why current is 0 for a large negative V-stop. I kind of already did that in the previous notes. Again, working backwards because that's the way the Mark scheme likes to do it. The stopping potential opposes the electron flow, reduces the current to 0 to the photogate. Let me switch back to black 1. And then the maximum kinetic energy of the electrons is less than the energy needed to transfer it to the collecting plate. In other words, to cross across the work function. And so the electrons are repelled from the collection plate and they can't make it. Again, because the maximum kinetic energy is Q times the stopping voltage, which is HF minus the work function. So as you increase the frequency of the light, you get nothing, 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 nothing until you have enough energy, enough HF to cut out the work function. That work function represents a loss. Once you hit that work function, now you can start to get photoelectrons off of the surface. And some photoelectric materials have a bigger work function than others. That's why you can't just like shine a flashlight on a plate of steel and then expect it to work as a photocell. And actually the materials that they use in photocells are difficult to come by. That's why photocells like photovoltaic cells and solar power is advancing, but not advancing as quickly as we would like, because the materials with very low work functions are hard to manufacture. Sadly. BII, we just discussed that before. Why does the current approach a constant value for a large positive V? Because electrons are attracted to the collecting plate. Every electron emitted, every electron, 100% emitted from the surface reaches the collection plate. So I could make that thing, I can increase the voltage and make it even more positive. I'm not going to get more than 100% of the electrons, right? And so that electron rate, it settles out at a maximum rate. And then the alternative explanation says that is a max number of photoelectrons that can be emitted per second because it's limited by the intensity, the rate of the photons, the energy per photon per time that is on the illuminated plate. It is not related to the applied voltage. Yeah, you can increase the voltage. You're not going to get more current. That's what I said. All right. C, calculate in electron volts. Ci, the energy of a photon of wavelength 430 nanometers. So we do Hc over lambda. And we have the lambda as 430 times 10 to the negative 9, but Hc as 1.24 times 10 to the negative 6. What they are hiding in there is the conversion factor. So that's H times C divided by 1.6 times 10 to the negative 19, and then divided by lambda gets us 2.9 EVs. And then for the work function, so that does check out. Then they want the work function of the metal surface, and so the energy is QV stop. We noticed earlier that V stop is 0.9 volts, or technically is negative 0.9 volts. Okay. And so the work function, we have energy is QV, which is HF minus the work function. We know that the QV from before is 0.9 EVs. We know that the energy of the photon is 2.9 EVs. It said that in CI. And so the difference being the work function is 2 electron volts. And that was number 5. And we're pushing up on 15 minutes because of my long thing all about the voltage versus current graph of photoelectric effect. I think it was worth it. So maybe this will actually be 4 videos instead of 3. But I don't want to make an extra long video because I don't trust Explain Everything not to screw it up. So stay tuned for 6 through 11. How many problems are there? 11. All right. So there's number 5. Thank you.